Hey guys, Professor Doney back. We're doing conservation of energy still. We're going to do just this last problem, the third problem for conservation of energy. Again, up here in the upper right in lovely green and pink, we have our conservation of energy equation. Energy at one point has to equal the energy other. And the three types of energies we've been talking about are potential gravity, potential spring, and kinetic. So we may have a combination of all or some of these, or only one of them, and have to equal that side. So let's come up with another problem. Let's start out with, again, a mass. We'll use 1 kilogram for the ball, and the one we're going to start out with here, let's have the ball, go away, sitting here loaded in some sort of spring mechanism. Now we're going to shoot the ball along a ramp, and then it's along this thing, and then it's going to go up this hill. Alright, at some point we expect the velocity is going to go to 0, and that'll be at the top. Okay, we'll call that the top. And partway up, though, we expect the velocity is not 0, so it will keep moving. So we're going to look at 3 different points here if we can get this in 5 minutes. We're going to call this point A. We'll call this partway up the hill point B, and that's point C. Now this, we'll say, is up at 4 meters. And the top, well, we don't know where the top is. We just know the velocity goes to 0, and obviously this is at h equals 0. We're going to use a mass of 1. Let's use a k value of 1,000 just to give us a good shoot on that, a good spring there. Stiff spring is going to push that ball there. Now, technically, since this is rolling, excuse me, we would have to look at the rolling rotational kinetic energy, but that's another chapter. So we can treat this as a ball or a block that's just going to slide with no friction. It's or like a puck on ice. It's going to go, no friction. We don't worry about the rotational. Okay? So we're going to have this block. We're going to release it, shoots the ball, and initially this starts out with some 0. So let's look at going from A to B. Okay, let's look at what's happening there. And we look at the energies we have at A. Well, we certainly have spring energy. Why? Because there's a spring. And do we have kinetic? No, because velocity is 0. That's right there. And do we have any potential to gravity? No, because we're at the height of 0. So all that spring energy is going to go into moving the ball to up to B. Now, what kind of energy does it have at B? Well, it doesn't have a spring, so there's no spring energy. It is above the ground, so there is going to be some potential due to gravity. And we expect it is still moving, so it's going to have some kinetic. So I'll have half kx squared here equal to mgh at point B plus half mv b squared. Okay, put some numbers in here. We get half. There's 1,000. Keep forgetting to tell you how far to compress it. Let's make it 1 meter just to make it easy math. There's 1 squared. Other side, 1, 9.8, height 4 meters, plus half 1 VB squared. Alright, if we can do this quickly here, that side is going to be 500, and that's going to equal whatever 16 times 9.8 is. 16 times 9.8 gives us 156.8. It's awful, plus half VB squared. Okay? And if we solve for VB, it's going to come out to be the square root of whatever that is. 500, 343 times 2 equals, and take the square root of that, it comes out to be about 26.2 meters per second, and that 5 minutes went really fast. But that's how fast it's going up the hill here. Now, for you to finish, how do we figure out how high it goes? Well, we set all that spring energy, which we'd have down here at A, and set it equal to mgh, all potential up at point C. And you can solve for h there. I'm not sure what that number is going to be. 500, oh, actually it's going to be somewhere around 50 plus meters. If you go through the math, you can check that. Running out of time. Hopefully that helps you look at a couple different there. See you next video.